Hello, ladies and gentlemen, herzlich willkommen, добро пожаловать, друзья. My name is Andrei, and in this video I will explain you how I create my high complex meshes, advanced meshes for openFOAM or other CFD programs like Ansys Fluent or Star CCM+. At first I would say a few words about my background. 2014 I was employed by Alstom Power AG. Now it's called General Electric Power AG. In this time I made my first steps with snappyHexMesh. After 2 years of testing, I was able to create high complex meshes for our tasks by Alstom Power or General Electric Power AG. After that I was focused on cfMesh, and after a while I was also able to create advanced meshes in cfMesh as well as in snappyHexMesh. Now you know that for creating my high performance or advanced meshes I use these two tools. First of it Snappy, and the second one is cfMesh. I don't want to talk much about the theory of Snappy and cfMesh, because if you open internet browser, you can find a lot of information about these tools. For example, you can find some videos, or you can visit official site of openFOAM and find mesh generation with snappyHexMesh utility. Or you can also visit cfMesh official sites and make your own study to learn how to create the mesh in cfMesh. I also recommend you to download some PDF files from the net. For example, I highly recommend you to download the final Andrew Jackson slides OFV7. This is a presentation which is about snappyHexMesh dict, beginning with block mesh dict, going forward to definitions, methodology. He is also described that snappyHexMesh dict contains of 5 main sections: geometry, castellated mesh controls, snap controls, add layer controls, mesh quality controls, and so on. At the end you can find also settings for mesh quality, and you can find also report of program what mesh quality control you have. And here's, for example, here are some settings that can be critical and not critical for mesh quality. As well, you can find the same documentation for cfMesh. For example, you can use a guide cfMesh version 1.0 or 1.1, and you can also scroll through it and find necessary information in order to create your own mesh dict, and start the meshing. To keep it briefly, I can say that these two tools are very powerful and let you create high complex meshes with other than 200 boundaries, like inlets, outlets, walls, and also it allows to create meshes with more than 100 million cells. Both of these tools create hexaeder dominant meshes, but cfMesh is also able to create tetraeder or polyeder mesh. In comparison of these two tools, I would say that Snappy has more control of settings like mesh quality and layer settings, and also can work with cyclic or porous zones. cfMesh in its free version cannot deal with zones or does not create high quality meshes but in general it is easier to set up because mesh quality or layer creation settings are automatically integrated in meshdict. In 90% of cases I work with Snappy, and only in 10% of cases of tasks I use cfMesh. Anyhow, I show you both meshing tools used on the same geometry. The geometry will be Mercedes-Benz W126. Here you are. This geometry will be investigated in our simulation. Here you can see more of it. Once we create the geometry, so we must start to edit this. I use for this task Salome Mecha. Here you can find official site of Salome Mecha, and here you can download a free version for example for Windows. Let me start the Salome. I started by pushing the button Run Salome, and it starts in a few seconds. Now Salome is running, and I open the prepared case, for example Mercedes-Benz steady state, and open HDF file. This is a study. Here you can find the geometry of Mercedes-Benz and also the air around it. What is necessary to know? Let's go through the process of editing of geometry. First, I have to import step geometry, which was prepared by one of the CAD programs like Inventors, Unigraphics, SolidWorks, Solid Edge, or FreeCAD. So I can import the step geometry, and then I have to edit this. Once the geometry is uploaded, the editing process can begin. I click with the right mouse button and choose the option Create Group. So then I have to select the option where the square shape is here, like this, and then I can select the geometry in total or choose a part of it. In order to make it easy, I select the whole geometry, and edit, and also I give the name for this geometry. It will be walls Mercedes-Benz 126. So I push the button and line close, and import the next geometry. This will be air around the car. Once the air volume around the car is uploaded, I begin the same operation. I create a group, but here I must to define more boundary conditions. I start with inlet, add apply, then I choose the outlet, press apply. The walls around it, I selected the walls around the car on the sides will be walls slip, and the wall under the car will be rod. I divide it in two parts: walls rod, and walls rod fine. I can select them if I turn away the car. So now I can select them and give them the name walls rod fine. Apply and close. So that's it. The geometry is prepared for export, and we export all of these parts, including the walls of Mercedes-Benz. Last operation in Salome will be to define the bounding box section. For that, we go into inspection, dimensions, and bounding box. I choose the object volume air, and this option gives you the min-max coordinates for each axis. These coordinates are necessary to create block mesh. That's all. I click apply and close, save, and then I go to export all of these boundaries. For it, I click on file, export, STL, and here you have some opportunities to choose the format as ASCII or binary. Here you can see the relative or absolute dimensions or resolution for STL file, and also you have to choose one directory where you do it. I do it most of the time on file order export, and there I export all of these boundaries, and it is the last operation on Salome. After editing the geometry in Salome, I go to my personal tool. It is Excel sheet defined by macro, and here I go through all settings which are necessary to create for creation of CF and snappy HexMesh digs. So we can start with the first step, and here I define my export file where the geometry come from. For example, everything is empty, rows and columns, and now I visit the export folder and give the path, copy and paste here, and then the STL preparation can begin. STL preparation runs automatically and gives in the name, according to their names, the boundary. Here you can see the boundary type, and here you can understand what each number means. On top we see that inlet will have number 1, outlet is number 2, and walls have the number 3 as boundary type. We can also have buffers, cyclic, army, processor, zone buffer, zone rotation, and so on. Let me show the snappyHexMesh dict sheet, and here I defined the bounding box. As you remember, I saved the min and max coordinates and give them as a box. Here I can also choose the global cell size. It is also needed to create a block mesh, and how my tool is working. If I define the global cell size, I can also see with that coordinates what would he have in bounding box, with that the dimensions of bounding box, and this global cell size we get 1,600,1.6 million cells. Then I compare, is it enough for me or not? And my wish is always that the block mesh has always approximately 1 million cells without any refinement and so on. So if I have 1.6 million, it will be enough for me, and I say 128 global cell size will be enough. Why I select global cell size 128? It's quite easy. We can look at the sheet bounding box, and here you see all refinements from 0 to 10, and each of them until refinement level 7. Example here in this case are integers. It's quite easier to handle with them because they are all integers. After defining of bounding box, we going back to STL preparation, and here I do some definition on each boundary. For example, I will say the inlet will stay cell size equal to global cell size, on the outlet the same, on walls slip I will stay also by 128 millimeters. Only the Mercedes-Benz STL files will be, for example, 4. It means here that edge cell size will be 8 millimeter, and the same I do with rod fine. It will be also 8 millimeters. This option is needed for edge refinement, and here in the next 2 columns, here and here, you have also the possibility to define the phase levels, refinement levels. I defined always as much as possible the same refinement level on face edges and on faces itself. each definition here is divided into definitions only for cfMesh, for example the column G, or snappyHexMesh. This is, for example, the column F. I have also mixed inputs for snappy as well as for cfMesh, and so I go one column after other. Last thing what I want to define here is a boundary layer. For example, I want on wall slip 5 boundary layers, so I have to edit also these columns, these cells which are now green. For example, if I have also some boundary layers, now 10 boundary layers on walls rod, I have to choose here what wall is what boundary layers have the priority, and here we see the priority number 1. So I click back to 0 and go forward on wall slip. Here you see relative size true or absolute size false. I choose always absolute size for boundary layers. That means during the geometry, the whole geometry, the cell size, the boundary layer cell size will be constant. So here I select the layer definition. I can choose 1, 2, 3, 4, 5. 2 means for us that boundary layers are defined by expansion ratio and first layer thickness. So we go back and define the thickness ratio. It is always taken by 1.2 in most cases, what I know. And here you can see recommended first layer thickness is 0.1 multiplied by the global edge cell size. Here we see the recommended max first layer thickness as 0.0128. I take it as it is, and here mean thickness factor is given for mean thickness, and it can be from 1, so we have max first layer thickness and mean thickness the same number, or I choose always 0.25. For most cases it's more than enough. Now I go forward to snappyHexMesh dict settings and show what I have also to define here. In this cell you see that convert to meters is equal to 1. This is a setting for bounding for block mesh dict. So we have these coordinates for bounding box. That means we take 5 global cells after each of these coordinate. 5. I can take 2, but I always take 5. So next step, we have to create after bounding, after block mesh, we have to create surface feature extracting. I give you here this parameter as true, and in surface feature extracting we have to define include angle and define right object, yes or no. Next step is decompose the particle. For these coefficient methods I choose always Scotch or simple So you can define here in X direction number of processor, and in Y direction, and as well for Z direction the number of here is the number of processors in total, and delta is defined here as 0.01. So the next on snappyHexMesh dict we have to we have to define castellated mesh as true, snap as true, and all add layers as true or false. So I let it as true. So then I have to define merge tolerance. It's always by 1 multiplied 1e minus 6. So as debug I take always 0, write final mesh only. At the next step we have to define the refinement regions. Now I want to show you my little bit in practice what the settings are mean, and I already created the snappyHexMesh dict by pushing this button snappyHexMesh dict create and other dicts create. But now I will open only snappyHexMesh dict and show you what we have already defined. So preform here is a snappyHexMesh dict file. So, and now we see that we have defined here we have defined castellated mesh as true, snapping true, and add layers as true. Then we define the merge tolerance and debug. So after that we go to the geometry. Geometry contains all boundaries which we exported from Salome, and for example it has inlet, outlet, walls, rod, and so on. The type is tree surface mesh. Tolerance is given by 0.0001, and the name is inlet, or other definition without extension STL. Another part of geometry is a part with refinement regions. In this case I selected only refinement box as refinement region, and refinement box is defined by I have choose here, I have to select here true, and define the number of refinement box, and then I have to define min and max coordinates for X, Y, and Z. Also define the distance to the center, and also the level. So I have to define also for example as true for refinement cylinder, and refinement cylinder is always defined by 2 points and 1 radius. I have also to define the distance, have to write the levels, and additionally I give the name as commentar for these refinement cylinders. For example, wheel front, wheel rear, and so on, and refinement level 4. For example, I show you here refinement box 1, refinement box 2, type searchable box, min and max coordinates, and commented out. I have the commentar. I also want to define the sphere. I have to define here 4 spheres. Number is here 4, and sphere is defined by center and radius. Also I have to define the distance inside and refinement level. And I give some commentaries on for better knowing way I have done the refinement. Now I have to go fast through the last 2 refinement zones. The first of it is refinement cone, and the second one is refinement hollow cone. The differences between them is that refinement cone has inner radius as 0, and in the refinement hollow cone inner radius is not equal to 0 and has some number. So the cone as it is defined by point radius and inner radius, and point 2 radius and inner radius too. So that we can also define the distance from the outside border or face into inside, and give also the commentator for that. So after the definition of refinement regions, I go to the STL file. I'll close the previous one only to show you how does it works. I go to STL files preparation, and click here on snappyHexMesh dict create. I also push the button other dicts create. It means that surface feature extract dict, block mesh dict, and so on will be also created. I go to snappyHexMesh dict and show you the difference. So you can see here snappyHexMesh dict defined refinement regions, and here you see refinement box, refinement cylinder, refinement sphere, refinement cone, and hollow cone. What is also necessary to know for me is the number of cells in which is closed by these refinement regions. For example, refinement box 1 will cause 1.6 million cells, and refinement box 2 will cause 2.5 million cells. The same situation is here by cylinder. The same situation, the number of cells is defined by refinement sphere, and so on. So let us go forward and go to the next step. Castellated mesh control begins in my snappyHexMesh dict with refinement regions. You only have to decide the mode. The mode is inside. It was defined here above. Refinement mode global or local, and refinement mode global is inside. So we have here everywhere the definition inside, and also the levels, including the distance. Let's go further. What is necessary to know about castellated mesh controls is what we have to define the max global cell size. Also, according to number of processors, we have now 4. We define the max local cells for each processor. Then we have to define min refinement cells, max load on balance, and numbered cells between the levels. This definition is very critical, because if we have too much cells and have also a number of cells between the level over than 1, it causes more and more number of cells. Another part of castellated mesh controls is the definitions of features and surfaces. Features mean that we have, after the running of surface feature extract dictionary, we have some features, some edges defined on your geometry, and all edges has different levels of resolution. So for example, you remember the walls on Mercedes-Benz and walls road fine I defined as refinement level 4. The next definition is refinement surfaces. Now we have here level 4 and refinement level 4 and 4. That means that inside and also on the edges, everywhere on the face of Mercedes-Benz 126, the resolutions will be, refinement level will be 4. Let's go to the next part of castellated mesh control, is resolve feature angle. Here I defined it as 30. It is standard definition, as well as planar angle. It's also the standard definition. And now we have to define the location in mesh. We can also define allow freestanding zones as true or false. For example, for meshes without zones, it will be false. And also we have to define the locations outside the mesh to find out whether we have leak. As you see, it's quite easy to go through my my Excel macro. Now we have here some snap controls. This is another part of snappyHexMesh dict, and all of these definitions are also standard. And smooth patch I defined always as 5, tolerance as 1, and solve iteration 30, and relaxed iteration, number of relaxed iteration as 5. So then we have other definitions, for example, and number of feature snapped iteration, and number of space slip intervals, and so on. Here at the last, at least, we have implicit feature snap, explicit feature snap, and multi-regional feature snap. I don't want to go much in the details. I only want to say that if implicit feature snap is true, then it means that snap will be done by using of resolve feature angle. Resolve feature angle is given here, and the implicit and the snap iteration and the snapping will be done by using of resolve feature angle. Explicit feature snaps mean that the snapping is done by using the feature block. Feature block is defined here. Refinement by here, feature block. So it's always true in my case, because I have always feature block and definitions of all of STL files. If we have multi-regions, the snap will be done by using refinement surface block. This is here, the next block after feature block, and it's always true in my case. Second last definition by creating of snappyHexMesh dict is add layer controls. I run fastly this definition and show you that all of necessary definitions are defined here. The last definition is mesh quality controls. The same situation here. We can define max non-ortho, max boundary skewness, mean wall, mean dead quality, and these definitions here defined as default. You can also define the best quality or best geometry relation. Doesn't matter. Now I have chosen the default settings, and they are enough to start the first case. And if something goes wrong, I have to define the better quality or for example better geometry. After the settings have been finished, I transfer them to cfMesh by clicking the button snappyHexMesh Dict Create. In this case, I have to go to cfMesh and look for the settings which were translated, and only what I have to do is to edit the refinement regions. For example, I take here the exported geometry refinement region and transfer them to the corresponding refinement region. The same here for refinement cylinder. So you see, I transferred all refinement regions from these lines to lines here, which are necessary for definition. And now I have to define all other presettings. I can also say that I want to have some boundary layers, and here I can also define anisotropic sources, workflow control, and at least rename boundary as false. That's it for all definitions in cfMesh Dict, and that's it for all definitions in snappyHexMesh Dict. Now we are ready and we can start cfMesh Dict creation. And the last one, we want to create other dicts. So I close this file and open this path. So I see here the block mesh, decomposer part dict, mesh dict, snappyHexMesh dict, surface feature extract dict. These are all necessary files for snappy or cfMesh dict. Let's go quickly through them. I can choose one of them, for example block mesh dict, and we see here the points. Then we see here the simple grading for global cell size, edges are empty, boundary are empty, and so on. So the next dict, what we can see, decomposer par, the number of subtype of processors is 4, method is Scotch, and simply or hierarchical coefficients are also given. Mesh dict or snappyHexMesh dict we already seen. It looks like that, and mesh dict looks here like this. Last thing I want to do here is to copy all of these dicts which we created and transfer them to external USB storage device. So we have CFD projects, Mercedes-Benz, and we save it here. The meshing process itself begins on the other machine, and it will be a Linux PC